The last thing that you write down is your guess or your estimated value. It might be a little different than somebody next to you because it's up to your interpretation, but it should be in the same kind of ballpark. Now, if the lines on a graduated cylinder represent the tenths place, if you see the tenths, now remember, if we're looking at a number, I'm just going to make up a number here. So if we see, I don't know, there's 45.6 milliliters. If we see those lines on the graduated cylinder, then our guess is going to be the very next digit we write down. So if it's right on the sixth tenths line, then we put 0 in the hundredth spot. We guess the hundredths. If it's halfway between the 0.6 and the next line up, 0.7, then we put 0.5 here. If it's almost up at the 0.7, then we change this 0.5, and instead we write maybe a 0.9. Oops, there we go. So 0.6 is what we see, and then we change it to a 9 in the hundredth spot. So basically, you see the lines on the device, write them down, and then your last digit that you write down is your guess. Okay, let's try this out. So here, I see the 12 and the 13. I also see these little lines. So this must be the 12.1, 12.2, 12.3, and here's 12.4. So I know it's between 12.3 and 12.4. Now I have to guess how far in between the two it is. It looks to me like it's a little less than halfway. So I'm going to write down, here's A, I'm going to put my answer here, 12.3, because I see that. And then I have to guess how far in between the 0.3 and the 0.4 it is. I'm going to say maybe 3/10 of the way between this line and that line. B, it's over here. It looks to me like it's not on the 4.1, this is 0.1, not on the 4.2. It looks like it's right on the 4.5. I see the 4.5 line, so I write down 4.5, and then I have to say, because this is what I see, I have to say what my guess is. And my guess in this case is that it's pretty much right on that line, so I put a 0 there. If it was a little bit over, like a little tiny bit past that 0.5, I would write 0.51. If it was a little bit more, I'd write 0.452 or 3 or something, but this is always my guess. And finally, let's do this one. Here's the meniscus. Remember, the bottom of the curve is the meniscus. You should know that. All right, so anyways, it looks like it's on the 30, and I also see the 31 line, the 32, the 33. So I'm going to write down that it's on the 30, and it's 0/10 of the way between, this is what I see, it's 0/10 of the way between the 30 and the next line up, which is the 31 line. So I'm going to say 0.0. That's my guess. So it's everything you see, and then followed by a guess. Now this looks a little messy because of the way it copied and stuff here, but hopefully you can read this, and I'll read it to you here. It says, explain the difference between accuracy and precision. Explain a scenario where measurements are precise but not accurate. So accuracy is how close you are to the accepted or true value. This is like making a basket. If I'm playing basketball and I'm shooting a free throw, I want to make it in the hoop. Am I doing that? Am I not doing it? If I know the boiling point of water is 100 and I'm testing a sample, am I getting exactly 100? Or am I off? So accuracy is how close we are to what we expect to get or what the true value is. If I give you a 20-question quiz, how many questions do you get right out of 20? Now precision has really nothing to do with accuracy. It's just, are we getting the same thing, same value over and over again? You know, do I take all quizzes this year and I keep getting 18 out of 20, 18 out of 20, 18 out of 20? Or am I all over the place? First quiz, I get a 18 out of 20. Next quiz, I get a 20 out of 20. Next quiz, I get a 15 out of 20. How precise am I? Precision is getting the same thing over and over. So if I'm playing basketball, if I keep shooting and I'm making the baskets time and time again, then I'm awesome because I'm accurate, I'm getting my goal, and I'm precise. But let's say I miss every single time and I just keep hitting the front of the rim, the front of the rim, the front of the rim. At least I'm precise. No, I'm not making the points, but I'm precise. The worst case would be to miss and then to be missing all over the place. Airball one, hit off the backboard another couple times, hit off the front of the rim a couple each side. I don't know how to fix that, but at least if I'm precise, then a small adjustment will fix it quite a bit. It's like if I'm measuring boiling water and I keep getting 98 degrees every single time, then I'm not accurate because I'm not getting 100, but at least I'm precise because I'm getting 98 every single time. Now, we looked at silverware from our drawers, and we decided, is that good to use to test or to administer medicine? Now, if a doctor or medicine says that you need 5, or a teaspoon, it basically means you need 5 milliliters of medicine. So if you take a teaspoon from your silverware drawer, it might not be exactly 5.0 milliliters. It might be above or below that. So it might not be accurate. And the way you fill it, you might fill it a little bit more one time, a little bit less another time, so you might not be precise either. So we should never use teaspoons from the silverware drawer for medicine because it's probably not accurate and you're probably not precise when you fill it every single time. Use a cup or measuring cup that comes with the medicine. All right, last 2 questions in this section here. It says, imagine that you calculate the density of a substance and it comes out to 3.45 grams per milliliter. So this is what you calculate. This is what you get. This is your experimental value. After checking the reference book, reference means it's going to give you the true value. You realize it should be this. This is the accepted value. So what you need to do is calculate the percent error. Now here's the formula. The only thing missing from this formula, because they're really hard to type, are the absolute value signs. Now you will get this formula on your exam, so you don't have to memorize it, but you have to know what to do with it. So the experimental value is what you got, so that's your 3.45, minus the accepted value, what you should have gotten, according to the reference book, so it's 3.60. You're going to divide it by the accepted value. The accepted is what you should have gotten, 3.60. So the difference up top is 0.15, that's how much you're off by, and then divide that by 3.60. And remember, it's the absolute value signs here. So don't worry about negative numbers, and you always have to multiply by 100. So when you do that, you should end up with about 4.2% error. Now remember, 4.2 is your error. So yeah, you're off by 4.2%, but you were really right about 96% of the way. So we always look at error, and error is a negative thing. So if your error is very small, this is small, that's good. You don't want a huge error. Look at this example here. It says, which percent error value is associated with a higher level of confidence? Percent error of just 5 or 95? 5 means you only have a little bit of error. 95 means you got a ton of error. That's not good. 5% error means we did it right 95% of the way. But if I have a 95% error, that means I only did it right 5% of the way. So that's not very good. So the lower the percent error, the better, closer to 0. It'd be awesome if you got 0% error. That means no error, high confidence in your answer, everything.